Hi, y'all. How you doing? Oh, thank you. Thank you. That was such a great talk. I really appreciated it. I'll see you all later. Thank you. OK, so this is totally reconfigurable engineering solutions, module abstraction layers. These are terms that I made up, so please keep that in mind. My name is Chris Gamble. I'm the head of hardware and developer relations at Goliath. So let's talk a little bit about what we're going to talk about here. First, we're going to talk about the problem space, of course. Then some of the things we've been building, specifically things I've been building live on camera, which is a terrifying thing, but is a lot of fun when you're about 2 hours into a live stream and I'm like, hey, someone's still here. That's great. And then finally, we'll look at like how if it works, did it work, can it work, I don't know. OK, so quickly about Goliath. Goliath is a SaaS IoT platform. Basically, all the things I build hardware, but we're not a hardware company. We are actually a cloud company, but we have open source hardware. That's the stuff I get to build. We have an open source SDK, which is built on top of Zephyr, which is awesome. And that's what I use primarily for all the firmware stuff. And then it talks to the cloud, and that's ultimately the Goliath product. But it enables cool things like OTA, data streaming, or data routing, and lots of cool things that you should all check out. So please do that, and it's very efficient and awesome. So let's talk about the problem we want to solve here. My problems almost always start with hardware. They start and end with hardware, actually. This is 2 different boards that we've been working on since the end of last year. Well, even a little longer than that. On the left one, the white board is the Elixir board. And that's got an NRF9160 and an ESP32C3 on it. Basically, it's an interface board to do reconfigurable hardware using like clickboards, and we'll show that a little bit later. And on the right side is the Astentis, it's called, but that's an e-paper display. It's got a Pico on it. It's actually an I2C peripheral, so it's easy to throw readings up to it, but ultimately we're not going to be talking about that here. OK, so what happens though if we're going to talk about the core, like the essence. Essence is actually all of the terminology you see. I somehow got into like the alchemy thing, and like all of the board names are alchemical, and so essence is another one. But basically, you think about like the processing core, the communications that are on the board. What if I want to swap that out? Because that's actually happened quite a bit before. Y'all remember 2022 and 23, the dark times, when you couldn't get any parts, and you're very grateful you're in Zephyr. You're like, I can swap out to parts. I just got to find one that's in there. So I did that a lot. Another time might be I'm trying to cost down a board. That's been a lot of my career. Maybe I want to try out a new IDE or try out something new, some new way of interfacing with a part. Or I'm just curious and I want to try out a new processor. So those are all common things. And then similarly, I want to maybe try out, this needs cellular because of some requirement for the end use case. Or maybe I want to switch to Bluetooth or Thread or all the things that Zephyr enables. So I want to make that really reconfigurable, but I don't want to necessarily design all the stuff. I just need I need every option, basically. And obviously, Zephyr makes that possible, right? Both on the comm side and on the parts, or really the microcontrollers, of what I'm really saying here. So some of the downsides, very obviously, I could go and just spin a new board. I could take the Elixir board, which you're seeing here, and I could just say, I could rip off that 9160. I could put on, say, ESP32C3 as the main processor instead of the side processor. And I could put the BG77 on there as the cellular board and use the modem subsystem. Or I could grab some NXP part and put that on there, right? And just all of these different things are different options. But each time you rip and redo, then you also have a new standard of doing that. So maybe we don't want to do that. It's duplicated work. It's slow. I'm not the fastest layout engineer. I mentioned 2 hours of live streaming. That's just a fraction of how much live streaming there is. And so what if we wanted to kind of consolidate that work down? So what if we took the modularity of a connector, which is what we often showcase in overlay files and similar, or maybe a shield. That's another one that we often see in Zephyr terms. And we want to make that a module, right? So this is not an uncommon thing in the space either, right? You often see module makers that are taking silicon from silicon vendors, many of whom are in the room this night, and they're often putting it onto a substrate. They're putting metal cans over it. They're pre-certifying it for RF, and then they're selling it because of the efficiency it offers. So it's basically that same idea. We're talking about that's here, but also some other things that might help us out here. So a module could kind of do this, and this is the one we're going to be talking about here, the one that is the output. So the downside to this is I'm starting from not a very well-constrained space because I'm just making it up as I go along. And so that means the size, there's no constraint on size. There's no constraint on what you need to have as part of the requirements. And there's really no constraints on which parts should go on there. So basically, I took the Elixir board, that white board you saw at the beginning, and I said, OK, let's take the essence out of that Elixir board, and we're going to put that onto the module here. So in this case, it's taking what was the 9160. I wanted to switch to the newer 9151, a little bit smaller. I still have the ESP32C3 as a secondary processor. So that's actually running in AT mode, so that I do like Wi-Fi locationing using that, which is super cool. And then I literally took a guess at kind of the number of pins I need and the size I need. Right? This is all subject to change here, but this is me making a standard as I went along. And so I was really optimizing for the use case that I had, which was replacing that essence of the Elixir board. So I knew that I didn't want to make it the most flexible board. I didn't want to put 100 pins on there and leave a bunch blank, because you often see that from module makers too. They often, you see reserved, and you're like, what does reserved mean? It means that they're allowing for future innovation, future changes. They don't know what's in the future, or they do know what's in the future, but they want to have a similar kind of footprint. And so I was just trying to keep things simple for the person that was going to implement this module later, in this case, me. So let's talk about what this ended up being. First off, I kind of defined some configurations based on, again, randomness, but also what I wanted to build. So I said the 9151, the ESP32C3 as the secondary offloaded processor. Then I kind of flipped the script. I said, OK, let's also make one with a NRF52840, which is a Bluetooth processor, but then a BG77 from Quicktell that uses some Qualcomm silicon, and that's going to be the kind of the secondary modem, right? So offloading that sort of thing. ESP, and that would be using a modem subsystem. You see that repeated a couple times here. Then let's switch it over. So the C3, which is kind of a smaller version from Espressif, that's the main processor, has Wi-Fi, Bluetooth, but then I could also turn on BG77 to do cellular. ESP32S3 is kind of a bigger version of that, and then Quectel's part for offloading. Not the most variety there, but I wasn't really going for variety so much as just use cases that I've seen in my own designs and stuff that I thought I might want to see here. That's great. But what that ultimately did is that started to then give me constraints. I needed to constrain myself. And so I already had the Elixir board, right, which is this starter board that has a bunch of peripherals on it and connections I need to make. But now I have a bunch of targets that I want to put onto this new Essence module. And that's where I started to pull these requirements from. So of course, like any good engineer, I went to a spreadsheet and started to compare and contrast, make sure it's all there. One thing that popped out very quickly is that, OK, well, if I do use the ESP32C3, which is a part that's low cost, and you'll see on a design a little bit later here, actually then you need a GPIO expander. And then that drives other requirements like, oh, actually, you can't assign a PWM PIM to a GPIO expander unless you buy the really expensive ones and the ones that aren't in Tree and Zephyr, which I also want to do. So like all of these things, basically, I'm kind of getting my arms around all of the different things that I need to do in order to make some requirements to make a module that ultimately allows me to talk about Zephyr, which I promise I will later in the talk here. Don't worry, I know I'm at a Zephyr talk. Excuse me. Again, this is this is a balancing act of what's on the module, what's not, right? So in this case, I talk about eSIM, or do I talk about it here? Yeah, I talk about it somewhere. But some of the kind of the bare, again, the essence. What are the bare minimum of parts that I need on there, and what can I rip off? Because we're going to be space constrained, we're going to be size constrained, and much of it is of our own making. So some of these things are trade-offs. I already mentioned the GPIO only. Really, I call it a simple GPIO. We do want an ADC. Many parts have ADCs, but we can't guarantee that we have 8 ADCs, right? Necessarily, even though some of the parts shown do have 8 ADC inputs. And then eSIM was a part that I had on there initially, but that's something that you don't always want an eSIM, or a lot of the new parts have secure storage where you can put your SIM information directly in as an iSIM, or you want a SIM connector. So again, you don't really know. You want to maintain that flexibility, but you don't really know what you need there. OK, so let's look at what ended up popping out of all this, because then we'll get to the Zephyr part, I promise. OK, so this one is the DRAM one. Again, the alchemical people apparently pronounce this DRAM, and so I did that, and also to disambiguate from someone saying DRAM, because if you see DRAM in the technology industry, you usually say DRAM. So DRAM 1. So this one is a 9151 with the ESP32C3. You'll also notice a couple other chips on there. There's external memory, something you pretty much want to have as an essential kind of thing, essence, and so that you could do over-the-air updates. You want to have and then also secure module on the side there, because even though a lot of these parts that I mentioned do have secure storage and secure ways to store private keys, I don't want to depend on that. You never know in the future, if you want to standardize, you could start standardizing on something like a secure element being external to the part as well, and they're teeny tiny, so that helps. In terms of requirements, you just have to have power, ground, and then you're going to program this over UART. All right, some other things you might notice is a gold thing around there. That's actually just me thinking, well, wait a second, you might want to take this through through FCC testing at some point in the future. So at least make sure I don't have traces going to the edge. So that was something I figured out much later in the process. That would be a custom shield there. And obviously there's an extra UFL connector. These are all UFL connectors instead of saying, like a lot of modules, you look at 2.4 gigahertz modules that are very common. They have inverted F antennas, they have chip antennas. I don't want anything to do with that. I want to make sure that it's like antennas are, that's whoever implements this sort of thing. And finally, space stuff. Okay, we have arrived. I've speed run through the hardware to talk about the Zephyr stuff. So now we have a module, right? And I've basically defined an abstraction layer around the edge of that module, right? So there's 38 pins. A bunch of them are grounds. I think there's 30 or 34 usable pins, and they're all defined. I don't know them by heart, but they're all there. But now we have to implement these in Zephyr. So what do we do here? Well, first off, I turned to my good friend Chris Wilson, who wrote this great article, which is the QR code here. And I asked him to help me with the abstract hardware. This is the article here, so I do highly recommend it. We actually use this on the Elixir board. So the Elixir board uses Microbus, which is a 16-pin standard. So you plug in clickboards from Microelectronica. Really great way to kind of have again, another abstract interface there, much like you might have with, you see a lot of Arduino Uno headers on dev boards and stuff like that. You can also do the same thing with your own custom abstraction there. In this case, we did Microbus. And so we're going to use some of that stuff here as well. So that article is a great read, and then you can also see how we do this here. So the lower right is the footprint that I used on both the module side, and then ultimately what I would use on the carrier board, because if you're gonna make your own module, you're gonna maybe manufacture your own module or buy it from someone else who makes it. You still need to land that somewhere, right? So the nice thing is, what you'll see in a second here is one of the ideas is that carrier board does not have to be complex at all. In fact, the reason we talked about this, the reason we had this, is the carrier board is as simple as a battery, a regulator, and an accelerometer, and then plus the core module piece, and you have, quote unquote, a product, right? It's not actually, it's not a product, but it's that level where you can now reuse this module and reuse these capabilities on the edge of the module to implement different functions, different application spaces. This is something Goliath does a lot with reference designs. And if you want to quickly turn that around and make a new thing, you can just reuse this core module over and over again. Okay, so first off is using abstract interfaces on the base or the module in this case, right? So this would be the DRAM module. So we're going to first use node labels. And so we're going to call it node I2C. Underscore I2C. And that's going to be something we talk about in the next slide here. But ultimately, this is basically just going to be a reference alias. That's going to basically be an alias that gets reused at that level. And then we're going to use something called GPIO Nexus nodes. And we're going to actually apply this to the different types of pins I mentioned. So we mentioned we have analog pins, we have simple pins, we have kind of more generic GPIO pins. And we're going to use that to assign to the different pins that are around the edge of the module, and then we can call those out later. So, and this is because we now are basically mapping the edge of the module to the GPIO. It's really a spreadsheet mess, but it's beneficial later, and you'll see that in a second. It's beneficial later because you don't have to think about what's on the module now. So you get kind of just the generic processing capabilities of a module, but you don't necessarily have to know which parts are on there. You're going to have to know that once you compile or once you kind of piece together all your overlay files, but you don't have to know it as the board maker using a module. Okay, so in this place, so the DRAM GPIO S160 is going to be mapped, and that's basically GP16S, is going to be mapped, in this case, on the 9151 to GPIO 020, or you often see P0.20 on those type of ports. So that's kind of then, that's how you're mapping edge pin, module pin to part pin. Okay, so now we are showing this kind of example I was showing here. The circular whiteboard is the carrier module. The module itself is the DRAM. And then we're basically mapping and saying that now we're going to use that DRAM I2C because we have just an accelerometer on here. We're going to hook that up so that the SDA and SCL are pulled through, and that alias for DRAM I2C is mapped to whichever parts are listed in the individual DRAM boards, right? So DRAM 1 is going to be tying together the DRAM I2C to the NRF 9151 I2C, and then it's all kind of abstracted out in that way. The idea being, though, now that we have the kind of pieces together there, we're only really writing an overlay for the whiteboard that is a shield, right? And that's the key piece. That was the key mind switch, is that it acts as a shield now because it is much like any other shield you might have on an Arduino interface board, right? You might plug in something that has a I2C-based accelerometer and not much else. Well, in this case, it's going to act in the same way. And so you basically already have a centrally created module abstraction for the different module versions that are out there. The DRAM 1 has its own set of files. And in this case, the white circular board, which, in case you're wondering, is called Sloshy McWashy, another live stream that Goliath did, for tracking of washers and dryers, whether or not they're done. That simply has an accelerometer and some power input, and that's all you really need there. And that has its own set of files that look like a shield. Okay. That was a long walk, but if you'd like to see an even longer walk, you can see this all live on YouTube. This is something we do pretty regularly. We do live streams every Wednesday and Thursday, or Wednesday or Thursday rather, and we also do some product streams every once in a while. So love to see you over there. That's all for me, and love to take questions probably after the fact. Thank you.